Imagine a massive planetary transmission system just spinning at like thousands of RPMs. If a single gear tooth is off by even a fraction of a millimeter, the whole machine just tears itself apart.
Yeah, exactly. I mean, when you're engineering at the absolute highest level, the terminology you use, it isn't just, a way to communicate ideas. It's the literal blueprint for whether a machine survives or destroys itself.
Welcome to a new deep dive. Today we're looking at a really fascinating presentation slide deck on precision mechanical vocabulary. And our mission today is to decode 5 critical engineering terms for you.
Right, because we want to reveal how this highly specific R&D and manufacturing language translates directly into the physical performance of these systems.
Exactly. Okay, let's unpack this. I want to start right at the beginning of the manufacturing line with how we actually carve these parts. The deck highlights this term, power skiving.
Yeah, so power skeeving is used to efficiently machine internal ring gears, specifically for ultra-fine gear teeth, what engineers call a module 0.5.
And there's absolutely zero room for error there.
Wait, none at all.
Right.
It basically combines the continuous, really fast-cutting action of hobbing with the extreme precision of shaping.
But structurally, how does it do both? Is it, I don't know, like peeling and slicing an apple simultaneously just to save time?
That's actually a great way to picture it, yeah.
Yeah.
You get the sheer speed of a continuous cut, but you keep the precise internal geometry of a shaper.
Oh, wow.
Right. So it's a massive leap in efficiency for those incredibly fine gears. But, shaping is really only step one.
Because the beautifully carved gear is still kind of raw. I mean, if we just threw that raw gear into a high-speed transmission, the friction alone would just cook it.
It would, yeah. Which leads logically right into the next process in the deck, which is lapping.
Right, lapping. That's using abrasives for microcutting. Yeah.
Exactly. What's fascinating here is the physical impact. Lapping cycloidal pins and discs achieves this incredibly precise surface finish.
Which practically eliminates friction.
Yes, completely. And, removing friction means removing heat.
Because heat means thermal expansion, which would just warp those perfectly skeeved gears anyway during high-speed operation.
Precisely. You have to remove that heat variable entirely. But, a perfectly smooth gear isn't necessarily a strong gear.
Right, because the moment you apply massive torque to the system, a smooth but brittle gear just shatters.
Yeah, and that's exactly why we need case hardening, specifically thermal processes like carburizing.
How does carburizing work exactly? Like on a chemical level?
Well, it literally bakes carbon directly into the outer skin of the steel at extreme temperatures.
Oh, wow.
Yeah, this physically changes the chemistry to form an armor-like shell on the outside while keeping the inner core of the metal tough and ductile.
So the sun gears in these planetary systems, they have to hit an exact surface hardness, right?
Yes, a specific microscopic tolerance of HRC 58 to 62 on the Rockwell hardness scale.
So it's a bit like a perfectly toasted marshmallow. You've got that hard, crispy outer shell to resist surface wear and tear, but a soft, flexible inside to absorb the violent mechanical shock.
That's a really good analogy, yeah. But unlike a marshmallow, this crispy shell has zero margin for error. I mean, if that hardness is off by even a single point on the HRC scale, the gear just snaps under load.
Wait, I want to push back on that idea of the gear under load, though, because even with a tough core and a hardened armor shell, when you apply enough force, the drive shafts are naturally going to deflect.
Absolutely. The geometry of the whole system shifts. And that exact physical reality is why engineers rely on profile modification.
Profile modification, so intentionally altering the theoretical, like mathematically perfect shape of the gear tooth.
Right. They literally shave a microscopic amount of material off the edges.
Wait, really? So they purposefully make it imperfect when it's resting, so it ends up being perfect when it's under stress?
Exactly right. They are anticipating that shaft deflection. Without profile modification, when the shaft inevitably bends under heavy torque, the gear teeth would suffer from edge loading.
Which means they'd literally be grinding their edges to dust against each other.
Yeah, exactly. By modifying the profile, the teeth mesh perfectly only after the shaft deflects.
That is brilliant. We've preemptively fixed the bending. But, individual gear perfection doesn't mean much if the whole assembly is just shaking itself apart.
Right, which brings us to the ultimate metric of assembly harmony. If we connect this to the bigger picture, we have to look at total runout.
Total runout. That's the measurement of the total surface area of the entire assembly during rotation.
Mm-hmm.
So what does this all mean? Like, physically, what happens to the machine if that runout metric is too high?
Complete chaos, honestly. In a complex planetary system, you need uniform load sharing. If the total runout is out of spec, the gears aren't spinning in perfect concentricity.
So one single gear ends up taking all the force instead of distributing it evenly.
Exactly. And when that happens, it violently fractures and the transmission fails instantly.
Wow. So for you listening, the big takeaway here is that in this high-stakes engineering world, vocabulary isn't just jargon.
No, not at all.
Terms like power skeeving, lapping, case hardening, profile modification, and total runout, they are the absolute physical prerequisites for a machine's survival.
They really are. And, it leaves you with something to ponder. I mean, if a microscopic profile modification or a tiny total runout error can destroy a massive planetary gear system, how much of our modern physical world is entirely dependent on anticipating invisible microscopic failures before the machine is even turned on?